of organizations that leverage advanced analytics is to develop ML products and rapidly bring them to production to generate business value. However, there are existing challenges when doing so. Raising appropriate infrastructure, automating process end-to-end, or even standardize ML products are big challenges, all of which contribute to many ML endeavors failing to deliver on their expectations. Today we're here to present a platform movement, LUPA, that was built at NOS in order, and we're going to present 3 chapters of its history. Its purpose is to accelerate advanced analytics, scale the impact of advanced analytics initiatives, while also managing technical debt. Today we present 3 chapters of our history. First, we go back to the past and we show what pains there were at NOS ecosystem that motivated and sparked motivation for this. We also present how LUPA breaks down ML architectures into loosely coupled ones, and also how they are plugged into our platform services, really inspired on the proposal of data mesh. And finally, how do we fit in an ML platform thinking? So first, starting with our ecosystem pains that we felt. A common orientation pattern that we see across organizations is to follow a functional-oriented process where teams are divided by expertise. For example, advanced analytics are siloed from other groups, such as data ops team, infrastructure teams, or operations. These create several pains emerge from this. First, deployments, the lead times of especially large deployments tend to be longer, as multiple requests need to be done in order to reach the deployment. And also, there are a lack of understanding or even visibility from the multiple teams into the work of ML product development. So this puts those elements into motivation and creativity vacuum once deploys need to be done, and therefore bottlenecks naturally emerge from this. At NOS, the main symptoms we saw was first a completely different approach where there was a lack of a platform or a self-served service that could be provided to accelerate all the teams. And not only that, but also we also saw models being thrown over the fence to a centralized IT team in order to do the deployment.
Yeah, but these problems not only arose between groups within the same company, it also happened between different squads of analytics within the company. And mainly, these problems arose due to the lack of standards. For example, both due to the repository templates and code structure not having standards. Starting by the repository templates, it meant an outside developer that wanted to understand how another squad tackled their problem and constructed their code. The first burden would always be to understand where data preparation was being made within the code, where train and inference occurred, and where the orchestration files were. Then, even if he only needed a simple solution, a simple code solution, it meant that he had no start or end point on the code where he could jumpstart his approach and his code reading. This meant that he had to read the whole code just to understand the context within which the squad implemented that solution and how the output of that code was used further within the code. And finally, there were also a lack of standards on column nomenclature. So, if 2 squads developed 2 data quantums, both with columns with the same name, let's say call day, for example, it meant that those columns could be computed in completely different ways. What this led to was the fact that for a developer to use a data product from another squad, it had to go inside the code of the data product to understand exactly how that column was being computed. All these problems were further compounded by the infrastructure the developers working on, starting by the problem of the data. If a developer wanted to use a data product that was already maintained and produced by another squad, the first step would always have to be to ask for permissions to access the database where that data was stored. This created a lot of costs of time for the developer. Then, machine learning pipelines could not communicate between squads. This was due to limitations on the infrastructure, meaning that a squad to reuse a machine learning pipeline that was already orchestrated had to orchestrate it themselves, meaning there were computations inefficiencies in this process. And finally, all of these problems were compounded by the simple fact that 2 squads with the same issue could tackle it with widely different tools. meaning that reusing code solutions was widely costly for the squads.
At the most core layer, we also found silos. So even within a team, we also found some sort of functional-oriented process. So data scientists and machine learning engineers had poor visibility over the data engineering work. So they basically send requests for their features to be developed, and the data engineers would develop and deliver them. Naturally, as any data quality issue arose, which they appeared, trust was a little bit damaged out of that. This was also compounded by the fact that both sides spoke different programming languages, and they could not really help each other and iterate quickly. Of course, rework or even bottlenecks naturally followed from this. Another problem that is also very well described in the Hidden Technical Debt in ML Systems, written by Discull in 2015 at Google, is the term of pipeline jungles. They are a case of glue code, and they often appear in data preparation. They can evolve organically as new signals are identified and new information sources are added. Without care, what was once a friendly ML project soon becomes a jungle of notebook scrapes, a join of notebook scrapes, joins, and sampling steps, often with intermediate file output. All of this adds to tech debt of the system and makes further innovation more costly. This was the environment that we saw at NOSH, and in an organic fashion, multiple developers of teams came along and paused and observed ongoing developments, and a platform raised out of it. This was how LUPA was born, in order really to accelerate the developer productivity, but in not a platform, but a developer and client-centric approach with a very attention being paid to the user experience of our developers. We really followed the main contributions of Zhamak Dagani, the introducer of data mesh, and also the core foundations written on the DevOps handbook. One of them is really to transition from functional-oriented teams to a different one, a different form of orientation where developers are optimized for speed, for responding quickly to the clients or the operations needs. So the developers need to be independent in an independent way to develop, test, and deploy to production. They do so by leveraging self-service services from a platform. This is where LUPA fits in, and it's being developed and maintained by an enablement platform team that accelerates other squads. From the platform side, our primary goals are to first accelerate lead times to restore and decrease failures, to decrease a lot the data and ML management complexity. So our developers need to write and read data and write or deliver data too. All the underlying storage is being taken care of. They need to request jobs to being computed and submitted by a cluster, usually through Spark, for example. We need to enable that, and also even to orchestrate pipelines or even guarantee data quality assurance. All of that is being taken care of by the platform. And finally, we really want to enable our developers to extract value from data and code, and also have a positive network effect throughout the entire mesh. In practice, we do so by creating what we call interfaces that our developers can plug into. They are very loosely coupled, and they have a specific function, and they happen through the use of CLIs, graphical user interfaces, or even reusable CI/CD pipelines that our developers can plug into to support their user journey. Finally, LUPA, you can see it as a platform where we connect to other open source tools, such that we are able to outsource that development to that open source tool. For example, we do not implement an orchestrator, we leverage Airflow for that. Also, from the developer side, LUPA establishes an API that creates automatically loosely coupled ML architecture. We do this through small components very well defined and described by the work of Zhamak Dagani on the data mesh, where she defined the term data product quantum. We seek to follow that same pattern. So the idea is that we have these, you can see it as microservices where they are independently deployed they have high functional cohesion, and they have all the structural elements in order to perform a function. They are well defined through 4 components. First, and Gustavo will describe it very well, the transformation code. This is where the developers develop their code and where they apply their aggregations, drawings, or filters. The quantum also has metadata attached to it, so its description, its identifier, and also a very well description of their inputs and outputs. It references data, so each quantum delivers with a given SLA data, and finally it is a really well defined the infrastructure or the platform dependencies in order to run the transformation code. It also has inputs and output ports. The input ports is where the quantum reads data from, and they trigger usually the transform code. These, at case of NOS, these are usually OLTP tables. And then there's the output port. The output port is where the transform code delivers data to. It can be an event stream, it can be a table, etc. At the case of NOS, we're talking really about tables that we write to. The data quantum is the axis over which our system can scale.
But what does this transform means in practice to the developers at NOS? It means that their work is not only streamlined, but is in parts abstracted from them. For example, as mentioned, both input ports and output ports are abstracted from the developer, requiring him only to settle down some basic settings. This means that the developer only has responsibility for what's happening inside the transform, and it can focus his total work on that. And it can perform any task he needs within this transform. For instance, if he needs to perform feature engineering through some data manipulation, he can do it inside this transform. If, on the other hand, it needs to create different training sets for experimentation, it can do it inside this transform. It can even use this transform to perform A/B testing between models to select models. In fact, this transform is abstracted to the point where both data engineers and data scientists can perform their work with it. What this means in practice for the squads is that once it comes the time for the data scientist to understand the work that was performed by the data engineer, he is solely focused on the job that was performed and the code developed by the data engineer. He's not worried about understanding the tools that the data engineer is using, because those are the exact same tools that the data scientist already uses in his day-to-day work. But our platform is not solely focused on streamlining work and abstracting things from our developers. The platform also makes sure that it delivers the best user experience possible to our developers. And we do this through APIs, CLIs, and GUIs, which the developer can use when it thinks it's the most fitted one to the task at hand. Let's imagine that he's starting by developing a new data product. At this point, he will start writing some code inside our transform, and after some time, you'll want to test that this code is producing data with the expected quality. To do this, he runs a simple command on the command line to make sure that the data quality standards that he himself set for the data product are met by his code. Then, when it comes time to train a new model with this new data quantum, which is fairly easy within our platform, it means that he can use the MLflow graphical user interface to analyze the results of the models that he has trained to select the best one. And then, once again, he goes back to the command line to easily deploy the selected model with a simple command to use in inference. We also make sure that we have the best user experience possible in mind in this inference step. We make sure that it is easy for the developer to, in a single step, both load the artifact of a previously trained model, perform inference, and obtain its predictions simply and efficiently.
We now arrive at our last chapter of our presentation, where we display a little bit how LUPA fits in the current MLOps atmosphere and follows ML platform thinking mindset. We know that premature optimization is an evil in engineering, but we are also hyper aware that understanding what are the main friction points of our developers is key, so that we are able to accelerate them. Common in ML platforms, 5 building blocks naturally emerge across platforms if we see the current atmosphere. Having a feature store, a model registry, a model serving, a model training, and data and model monitoring is common building blocks that we see. In our case, we understood that the main needs of our developers and friction points were around data preparation and feature engineering, where how can I keep the same train and serve pipelines, how can I guarantee data quality, and even how can I really orchestrate and automate the entire process end-to-end to generate predictions and have an impact on the business value. With this, we chose to first tackle the feature store and the model serving to give us the most value. As we, regarding our feature store, we will, in the next slides, go a little bit further on the enumerated advantages. But keep in mind that what differentiates us from and our platform from others is really our data mesh-oriented idea, where our data quantums are really the backend of our feature store. Its main benefit is to break down, as Jean-Marc Degani talks a lot and really well about this, the data quantum have the potential to break down completely labyrinth pipelines throughout your advanced analytical use case. So you have the complete lineage from your model, from your sources to your model, and what features they use. And furthermore, you can have a lot of observability regarding, for example, what quantum is having the most cost, which one needs to be more fine-tuned and optimized because its transformation code is not really, it's taking too long to compute. Another advantage is to reduce train and serve skews. So a common pattern in ML product development is when we are generating models is to to couple our feature engineering code to the generation of those models. These have several problems. For example, when you are shipping to production, you need to basically ship that same feature engineering code to the serve pipeline in order to obtain the same model predictions. This creates a moment where errors and mistakes can be made when doing so. You can also tackle this with other alternative approaches where you package that same feature engineering code and you reuse it within that project. However, that can be used in a local way within that DS team. But if you actually have decoupled it totally, for example, through a micro pipeline with this data quantum, you can make it really reusable across teams. Furthermore, really coupling that feature engineering code is something that we saw not going really well, because we understand that business owners want to sometimes move the investment from one use case to the other. And if you couple those two together, if those features are very useful for other projects, they die within that use case, and you not extract them to other use cases for usability.
We also make sure that we help developers avoid a train serving skew. And we do this through easy time travel. What this means is that in training, the only thing that the data scientist has to do is to select the time window within which it needs its data to perform the training. Then, on the inference step, it only needs to select again the data it needs for the inference, be it the last day or the last week. This means that both the training set and the inference set are originating on the same data quantum, implying that the data on both does not have any discrepancies in these two sets. This easiness of time travel also ensures that it is easy to fix mistakes in the data. If a developer identifies a problem with the data, let's say a month ago on a specific date, it can easily run just that day to fix the data. It does not have to run the whole data quantum, ensuring computing efficiency. And finally, this also translates into a much better user experience for consumers of this data downstream, both for the exploratory data analysis, where it's very common to filter a single week or a single month to perform some analysis, or even to use as input for other data quantums, where you can easily filter out only the data that you need from this data quantum to feed to the other data quantum, ensuring that you optimize at maximum the running time of your code. And finally, our feature store also ensures that data is standard and interoperable. This means, first of all, having compatibility between data quantums and orchestration pipelines. It means that both data quality and pipelines are visible and accessible to the developers to ensure maximum trust on the process. And finally, that data quantums are easily discoverable by developers. And our user experience also ensures that our model serving is made easy to developers in a single step to load model artifacts already trained and perform inference and predictions. However, you can build the best tool ever that is useless if no one else is using it. Fortunately for us, our tool has seen a very good significant adoption rate. We already have more than 10 squads using the platform, more than 40 developers, which translates into an adoption rate of around 60%, meaning we already produced around 200 data quantums with our new platform. And to finalize our presentation, we would like to leave you with some of the key philosophies that led us through the development of this platform. All of these key points arose due to the problems that we were discussing with the ecosystem when we first started the platform. However, as you might know, not all cornerstones are born equally. And we make sure that, foremost, we always keep in mind that we are always trying to accelerate squads that can independently develop, and that we are always ensuring that we have a client-centric approach to our platform, ensuring that the user experience is always the priority. Thank you.
Thank you.
Yeah, thanks for the presentation. So we have a couple of questions. First, I wanted to ask, maybe I missed that, what did you actually use for implementing your feature store?
Oh, sorry, what?
What did you use for implementing your feature store?
Okay, the vision of LUPA is not really to leverage one platform. For example, there are open source. For example, Tecton is a software that is a platform itself that can already do these kind of things. Our idea is a bit different. We want to reuse open source tools that enable us to do so. So, for example, Airflow is a key tool for us to our feature store is an offline one, so it works in a batch process way. So Airflow is very important for us to generate backfills on the fly. And regarding the compute, it all runs almost in Spark right now. Mm-hmm. And we, for example, so Dataproc is something that we use right now for our cloud. We also built an on-prem one, which was a bit different with Yarn. But I would say that Airflow, Spark, great expectations to understand data quality are very, very important within our features.
And for the storage layer?
On the storage, BigQuery. And on the on-prem one, also, we used HDFS for that, Hive HDFS.
Okay, thank you. So, question from Joshua. How did you measure the effectiveness of your platform? Did you use any metrics for that?
Yeah, I think one of the key metrics that we were using was trying to track how many developers are actually using the platform. Because it is very important for us that developers leave the previous ecosystem to use our platform. This means that the platform is actually helping them reduce the time that they need to take to the production or the time that they need to maintain the data products that they already developed. This is the main way that we track how effective we are being with our platform.
Yeah, I think you mentioned it's like 10 teams use it, right?
Yes, yeah. Exactly.
I would like just to add a quick note on that. We're still working on it, but something that is really important and we're trying to work is, so the ownership is spread around the data product teams. And we want to generate KPIs for our data quantum, for example, data quality, or, this data quantum is failing to deliver with a delay of 15 minutes. So those are a lot of KPIs that one can build for their features as well.
And, a question from André is how disaster recovery friendly is the platform?
Sorry, what?
Like if something happens with the platform, like there is a disaster, like how friendly, like how easy is it to recover for the platform from the crash?
So we do not put ourselves on. We create services that can accelerate productivity, but we are very aware of not blocking anyone, or if we are putting ourselves in a block step, for example, because you require a given access. For example, we have a lot of pull request CI/CDs for you to deploy, but we are very agile in order to perform that support. And like the times to restore, if something fails, it's not really longer than 1 day at most. So we are very quick and agile in order to not really block anyone. That is really important.